Alright guys, so what we're doing today is it's called optimization problems. This is on the notes packet that I just gave you. This is section 3.7 in your book. So what we're doing is we're trying to find solutions to problems that require an optimal solution. For example, if we have a business, we're going to want to, let's say that we're having canned foods that we're producing. We would like to minimize our costs. And one way to do that is maybe we have to have a specific volume for the can, but we want to minimize the cost to create the materials for the can. So we would want to minimize the amount of materials, such as the tin that it takes to make the can, the paper that goes around it. So we would want to minimize that surface area while keeping the volume constant. Okay? Another example of this would be, let's say we're making a fence. Okay? And we've got, say, 100 feet of fencing, and we want to have a maximum area in our backyard. Well, we want to know what do the dimensions need to be in order for that perimeter to be 100 feet, but to have a maximum area. That's the kind of thing we're going to be looking at. So the process we go through for this is we need to write a primary equation. What is it that we're trying to maximize or minimize? Then we're going to have to think of some secondary equations. And we always want to have a single independent variable. That means we're going to do everything in terms of x, no y's. Determine values for which the stated problem makes sense. For example, back to the fence example. If I come up with a negative answer, that couldn't work, could it? Because we're talking about the amount of fencing we're going to use. Then we're going to use calculus techniques to find the max to the min. Let's look at this first example. Find two positive numbers whose sum is 140. And whose product is a maximum. Just to kind of understand what's going on in this problem, tell me two positive numbers that have a sum of 140. Any two numbers? Okay, 70 and 70. And that would be 4,900. Somebody said 80 and 60. That product would be 4,800. What about 140? What's that product? 4,000. Okay. Of these, which one had the maximum product? 70 and 70. But we can't really prove that's it. We haven't checked all the options. We haven't checked 68 and 72 or 75 and whatever that is, 65. Okay. All right. So let's look at the problem now. So find two positive numbers whose sum is 140 and whose product is a maximum. So we're talking about two positive numbers. We're going to say x equals the first. So x is the first number. If the numbers have to add up to be 140, look at this pattern. My first number was 70, my second number was 70. My first number was 80. How do I find that second number? Subtract what? Subtract the first number from what? 140, right? So that's the pattern that I would use. My second number is going to have to be 140 minus that first number. Right? Isn't that always how I would find the second number? If you can't figure out what this is, make this little chart. Think, if I know the first, how do I find the second? I know it's 80. How do I find the second? I subtract it from 140. Okay? So here would be our two numbers. Now, what it is we're trying to maximize is the product. To write the product of these two numbers, I say P equals my first number times my second number. That's what we call the primary equation. That's what it is we're trying to maximize or minimize. I like to do this second. Our book tells us to do it in this order, but I always come up with this first and this second. It's easier. Okay, so now we're going to multiply this out. We get 140x minus x squared. This is the function for the product. How do I find a maximum or a minimum? What does the slope have to be if I have a maximum or if I have a minimum? 0. What finds the slope for us? The first derivative, right? So we're going to take this first derivative. If I take this first derivative, I'm going to get 140 minus 2x. What do you think I would do now? Solve it by setting it equal to 0. Solving this, I get 2x is 140, x is going to be 70. So this is what we call a critical number. Now, I don't know for sure yet that that actually is a max or a min. Here's how I can check it quickly. Let's take the second derivative. What's the derivative of this? Negative 2. That tells me, because my second derivative is negative, that it's concave down, always. If it's concave down, and this is where the slope is 0, does that force this to be a maximum? Yeah. So now I know that my first number is going to have to be 70, and my second number is going to be 70. And we prove that, okay? I'm not saying that, of course it's easier on this one. We know it's going to be 70 and 70. But if I asked you to prove that it's 70 and 70, you would have to prove it with calculus. Or else you would have to test every single number that's possible and show that it's the greatest product. Okay? All right, let's look at the second one now, a little bit more complicated. The product of two positive numbers is 192. The sum of the first plus 3 times the second is a minimum. Okay, sometimes it's hard to get started with what are our first and second numbers. Your first number, you're always just going to call x. Now, the two numbers have to have a product of 192. So let's say that first number is 2. Well, then that second number would be 96. All right, let's say that first number is 4. My second number would be, dividing that, 19 divided by 4 would be 4 with 3 left over, 48. What am I doing to find this second number? I know they have to have a product of 192, so what am I doing to this first number and the product to find the second number? Dividing, yes. So what's the second number going to be then in terms of x? Good job. 192 over x. That's going to always be our second number. It's always the opposite. See how, guys, on this one, it was the sum, and we used subtraction. This one is the product, so we had to write division. Okay, I'm trying to explain why that happens. Now we have to look at the rest of the problem. This is our primary equation. The sum, which we don't know what that sum is, of the first, here's our first, plus 3 times the second. See how I did that again? We want the sum to be of the first plus 3 times the second. So this is what we call that primary equation that we're going to have to figure out. All right, so to do that, I'm going to want to simplify. So I'm going to have the sum as x plus 3 times 192 is 576. In order to take this derivative, I'm going to have to rewrite it like this. I want to know, where do I have a high point, or in this case, a low point, because I'm trying to find a minimum. So I want to have a low point. So the derivative is going to be 1 minus 576 x to the negative 2. This is my slope. What's the slope at a high or low point? 0. So I'm going to set this equal to 0. So I'm going to take this over to the other side. 576 over x squared equals 1. I'm going to cross multiply. X squared equals 576. That's going to be plus or minus, 24. Yeah, 24 is the square root of 576. can we have a negative answer? Look back at the problem. No, it says positive, so I don't have to worry about the negative. So 24 is my critical number. I want to make sure it's a minimum, so I'm going to take the second derivative. If I take the second derivative, I get positive 1,000 something. I really don't even care what that is. Positive 1,000, just to be more exact, I'll do it. 576 times 2. Okay, so 1152, taking this derivative, x to the negative 3. There's my second derivative. If I plug in my critical number, do I get a positive or a negative number? Positive. So if my second derivative is positive, it's concave up. If it's concave up, is that going to make this be a minimum? So now I've proved that. So my first number is going to have to be 24, and my second number is going to have to be 192 divided by 24, which is 8. Any questions on that? All right, we're not going to do this one. If you come across one on your homework that has to do with the closest point and distance, we're not going to deal with that type. It's pretty tough. You're welcome to figure it out if you'd like. Example 3. Find the length and width of a rectangle that has a given perimeter and a maximum area. Is the bell going to ring? No. Oh, perfect. We have time then. Okay, so we've got a rectangle. Find the length and width of a rectangle that has the given perimeter of 120. Now, guys, think about this. The perimeter must be 120. I'm going to call this x. If the whole way around is 120, what are any two sides going to add up to be? 60. So if this is 10, this is 50. If this is 20, this is 40. So how do I state what this side's going to be in terms of x? Say it loud. 60 minus x, right? You guys get that? If this is 10, this is 60 minus 10, 50. If this is 20, 60 minus 20, 40. See what I mean? Remember how I said these two have to add to be 60? So to come up with this side, it's 60 minus x. All right, find the length and width so that we can maximize the area. How do we find area of a rectangle? Length times width, base times height. So it's going to be x times 60 minus x. I'm going to multiply that. Take the derivative. What do I do once I have the derivative? If I'm trying to find a max or a min? The slope needs to be 0. So I set this first derivative equal to 0. And we get 30. I want to make sure that this is a maximum. It could be a minimum. I got to double check and make sure. So I'm going to take the second derivative right here. The second derivative is negative 2. Second derivative is concavity. So what's true of this? It's always concave down. If it's concave down, what's going to happen at that critical number? We're going to have a max. So this is going to result in a maximum. So our maximum is going to be when our length is 30 and our width is what? 30. So what does this rectangle just happen to be? A square. Is a square a rectangle? Always. Is a rectangle a square? Not always, but sometimes. Okay.